Okay, guys, so welcome to the 10th Robotics and Artificial Intelligence Meetup. And nowadays we are doing it at 7 p.m. instead of 8 p.m. because in India it gets really late when we do it at 8 p.m. And the topic for today's meetup is cart pole balancing using reinforcement learning, specifically temporal difference. One of the techniques of reinforcement learning will be discussed today. And the agenda for today is such that after my introductory presentation, which would not be longer than 5 minutes, I'll begin with the presentation of the project, and I'll take a full case study and explain all the underlying concepts, and also go through the code base briefly. And after that, we'll have a Q&A discussion. We can have a discussion about the topic and the project that was shared, and also you can ask doubts or stuff that you have. And after that, we'll have a quick feedback session. So there are two phases of this feedback. One would be feedback for the presentation, and one would be feedback for project process. This would be important because since we are doing it every week, we only want to do it better every single week, so that we develop an efficient system of utilizing these 1.5 hours more efficiently. And after that, we'll have a project accountability share. So if anyone has done a project and wants to share his progress, this is the time to do that. And after that, we'll have normal introductions and casual networking like we do normally. And after that, I'll make a quick announcement as well before we wind off the meeting for today. All right, so I don't think I need to go into details of these slides. I'll just quickly mention that we are focusing on robotics, artificial intelligence, and also experimenting with new ways of learning, and so edtech and entrepreneurship comes into picture. And the way we learn is that we conduct weekly meetups and also monthly research paper discussions, out of which one has already been done. And we also offer project accountability. And the weekly meetup format that we have is such that what I'll do today is I'll just quickly go through what the goal or the objective for today's session would be, and then I'll define the problem, and then we can have a good discussion, a good brainstorming session where we can all ideate on that problem. And after that only I'll be sharing my own solution or for this particular project or case study. And I'll also be sharing the algorithm today. It's not very advanced. I'm just starting with beginning, and if reinforcement learning is something that a lot of people are interested in, then we can continue with this series with slowly building up on slightly harder projects and stuff. Yeah, and then another thing that I've included this time is that we can probably have a task for next week. So I'll share the code base, and maybe some of you have time and you can try to run the code and write it from scratch. It's a very small Python script, and you can share your progress next time, but this is totally optional. And after that, I'll share the concepts covered, and like we did in the computer vision meetup, except that we'll have a very small portion today and only pertaining to the concepts that are relevant to this particular project. Yeah, we'll also have a concept discussion section after that. And the reason for that is that we want to learn only the concepts that are presented in the project, so we know how these concepts are actually used. And these are just the templates for those who would want to volunteer for a project. And talking about volunteering, so I request those of you who have some interesting ideas or projects to share to please volunteer for our meetups and research paper reading sessions, because the more people volunteer, the more different kinds of ideas we have, and it's always better to learn from different perspectives rather than a few people sharing the presentation every time. So yeah, let me know if you would want to volunteer, and I can fix your spot for next week. All right, so let's start. Yes. So, as I mentioned, the problem for today is cart pole balancing using reinforcement learning, and this is how we would be flowing with the steps. So, the goal of today's project share is that we learn a few fundamental concepts of reinforcement learning. So I'll be defining the reinforcement learning problem, what are states, actions, rewards, expected rewards, policies, and also briefly about value function and discretization of continuous spaces and how temporal difference works. So this is like very beginner friendly, and so if you have no experience with reinforcement learning, I think this should be a good starting point, hopefully. Yes. So coming to the main problem now. Yeah, so this is, as I mentioned, the cart pole problem. See, looking at the image here on the right, we can see that we have a cart here, and on it, connected using a revolute joint, we have a pole. So the problem that we want to solve is that we want to move the cart such that the pole is in a vertical position. So we want to balance this pole on this cart. This is the cart pole problem. So what is given is that the cart moves linearly. So x is the variable which determines its movement, and the pole rotates, and it is the angle with the vertical axis of the pole is given by theta, and the task is to balance the pole by moving the cart. So the movement of the cart is under our control, and by balancing the pole we mean that we want to keep this angle within a certain limit. So if the angle exceeds, I've taken like randomly 12 degrees here. So if the angle exceeds 12 degrees, then that's out of balance. So we want to keep it within 12 degrees. That's the problem that we have, and the control parameter is the cart movement. Okay, so the requirement is such that the episode would end when we have the angle greater than 12 degree, and the movement of the cart greater than equal to 2.4 degree. Now this is these values I've basically taken from a course that I took. I can also provide reference to that at the end. And the main idea is that the episode should end when the pole is out of balance. So when it is not balanced, then the episode should end, and it should reinitialize and start the training process again. And likewise for when the cart movement is out of range. Now what do I mean by out of range, and what does episode mean? So these things are like very basic stuff, and I'll be going to the fundamentals of reinforcement learning and defining the problem so that this whole requirement set actually makes some sense, right? Till now, does anyone have any question? Mathematical equations for that, for what? Yeah, exactly. Yep, exactly. Yeah, that's the idea. Yeah. All right. Okay. So going to the fundamental concept of reinforcement learning. So if you're already familiar with reinforcement learning, the idea is actually very simple. So we have an agent, which is generally either an algorithm, a robot, or anything that is taking some sort of action on the environment, and the environment is something that is external to the agent. And the agents essentially represent the brain of the system, the decision making part. it does some action on the environment and changes the state of the environment, and as a result we get some reward. So let's briefly look at all of these states. I've also mentioned policy here. So what does that mean? So the agent is basically the decision maker, in most cases an algorithm that we would be defining, or simply a function even. uh, and the environment or the world is something and that is external to the agent. State is a complete description of this particular environment or the world. And there is another term that I would want to like briefly touch, is called something called observation. So observation is something that can be partial as well. So when we have like partial data of the environment, it can be considered as an observation. But a state is always something that completely describes the world. And action is, of course, the action, the step that the agent takes. The reward is essentially something that tells us how good the state is. And the idea is that the agent should take an action on the environment, change the state, get some reward. And the overall problem of reinforcement learning is that the agent wants to maximize its reward, right? And the reward is something that is designed to solve a particular goal. So for example, for our problem we would have a particular goal, and we would go to that as well. And the reward is always designed such that we want to achieve a goal. And the policy is nothing but a mapping of states to action. So given states, what would be the probability of selecting an action? So like there are two types of policies actually. One is deterministic policy, which is maybe, for example, 0 or 1, or if it is a probabilistic or a stochastic policy, it can range from 0 to 1. It could have any values in between as well. So policy is essentially the probability of selecting an action given state. And we mentioned episode. So an episode is, I think now it should make more sense, because episode is a sequence of these states, actions, and rewards. And every episode must end with a terminal state. And a terminal state is also defined according to the required goal. So that's the overall reinforcement learning problem. Now back to our problem and how it fits to the reinforcement learning case. So we see that episode ends when basically the episode would end when the agent balances the pole for at least 200 steps. Now this is again a number. You can also take maybe 100 or 150, and you can experiment with different things and try out. For this particular problem, I'm taking 200 steps. If the agent learns to balance the pole for 200 steps, then we should be fine with the problem. Then the problem is solved, and we should end the episode. We should end the episode in three conditions. One is when the steps is greater than 200 and it's balanced, then the problem is essentially solved and we should be ending the episode. But there are two other cases which are not ideal, and when the theta, the angle is actually not good enough to keep the pole straight, so we would end the episode and we would try again. Same for the movement x basically. All right, now let's have some discussion. So based on this very simple idea of reinforcement learning, I hope that made some sense. Now what we will be doing is we'll be having a quick discussion and trying to define state, action, reward, and policy. So here I would encourage your participation, and maybe you can make your guesses of how we can probably represent the state of this system. and how we can define the action, what kind of reward we can take, and policy. Any guesses, any vague guesses, or anything would be fine. There is no wrong answer. Okay, so you want to define the state as x and theta. So you want to take these two variables into account. Okay, yeah, yeah, yeah. That's a good definition of a state, and that's definitely valid. And any other guesses? Uh, that's like a different way of defining it. So you want to, sorry, can you repeat? You want to define one of these parts as the environment, and the other one. Mhm. So you want to define the state as theta, and the action movement. So this particular variable and movement you would be using as action. Mhm, mhm. So this is not like, this is not defined at this stage. This is what we are trying to do. So you want to define basically x as the input, and theta as the output. Like so one valid solution that we had till now was that we can have both x and theta as the state, right? Yeah. And another thing that someone mentioned now is that we can have x as the representation of the action, and theta as just for the state. Um, but actually, like, what is the action? So in this particular case, I want to try to understand how you're defining it. So what would the action be? Okay. Yeah. Yeah. Okay. Yeah, the linear movement. Yeah, that's definitely right. Yeah, and I mean this is perhaps also valid, that we can represent the state as just theta, right? I don't know if the results would be good or not. Probably this is something that can we can like try out experimentally on a program, but it does seem valid, I think, if I'm not wrong. And yeah, any other? Yeah, exactly. Mm. Mm-hmm. Okay. Mm-hmm. Mm-hmm. Yeah, let's keep this as well in mind. Any other solutions anyone wants to share? Uh, any crazy ideas are also welcome. So, like one idea that can be is that you can use images to capture and somehow use pixels, the state of the pixel arrangement as a state as well, like something along that line uh, can also be valid. So maybe you can think in that direction, or any other ideas that you have. Yeah. IMU, what exactly, which parameter do you want to measure using IMU? Yeah. So, yeah. Yeah, exactly. Hmm. Yeah, I mean, for this particular problem, let's not go into the sensors, because then, I mean, yeah, that could be a different, we would be taking a different direction. Let's just consider it a simple mechanical system, and let's not go into how we are measuring theta and x, and we just have theta and x. Let's take this into account. Yep, exactly. Yeah, so we want to keep this as straight as possible, and the angle within 12 degrees. That's it. Yeah. Yeah. So any other solutions you can think of, and what would be the reward and the policy? We haven't talked about this. What should the reward be? So our goal is to keep it almost straight for around 200 episodes. So how can we easily define the reward? Okay, so the reward part is not clear, huh? Yeah. The reward is, maybe I can go to that slide again. Yeah, I think in this slide I haven't explained it in detail, but as we go through the problem, it will become more clear definitely. So, the reward here, as I mentioned, is it tells us how good the state is. Now, what does this mean? When is a state good, according to you? Uh, so a state would be good, or an action taken would be good when it is towards a goal, towards the goal, when it brings us closer towards the goal. So in reinforcement learning, everything we do is to achieve this particular goal. So this reward should be designed such that we get a good reward. Let's define a variable reward, right? And we increment this value, or we increase this whenever we realize that the state is something that is bringing us towards the goal. That is like an abstract idea, and how it will be implemented in the code, I think as we go through the process, it will make more sense. But does it make like theoretically, does it make sense what a reward is supposed to do? Yeah. Yeah, exactly. So the actually not after, and that depends on how you define it, but ideally after every step. But I have a slide that explains reward as well after that, so don't worry about it. I think it will be clear. Uh, um, yeah, and we can still try to define what a reward would could be. So think of like what our goal is and try to derive that for this particular state what could the reward be such that it brings us closer to our state. So but for that you have to keep like I think one state and one action into account. So let's fix for example x and theta as a state for this particular case, and for action also the movement of x. So let's just take this as one of the persons proposed. Let's just take this and try to now uh, define the reward somehow. Mhm. So both of these things are you have also defined as the state, but so I think the concept of reward is yeah, I think I need to probably cover it in a little more detail so it makes sense. Mhm, mhm. Okay. Mhm, mhm. Yeah, yeah, exactly. I mean, exactly what we define. So you can keep it as simple as doing +1 or -1 when it is when the state is good, basically. That is totally a valid solution. Yeah. So you would be defining it basically. Yeah. Hmm, hmm, hmm. So again, you can define it. So again, you can define it. You can actually define it that okay, if the angle is greater than 12, let's give a negative reward, or maybe you can just give a positive reward whenever the angle is within the range. So it's up to you totally to define it, and how it will perform is probably something that only after running you can see the results. Yeah. So you can actually define the state as simply x as well, although that wouldn't probably make sense. But you can define the state as x theta. You can define it as x and the velocity of cart and pole angle, and you can define it in multiple ways. Maybe even take the second order terms acceleration into account as well. If you, yeah, that's totally possible. Uh, So the point of this discussion is to just have a brainstorming session and try to understand, try to get different solutions. Otherwise, if I just share my solution, then it would just bias and we would not be thinking. So yeah, you can define state in multiple ways actually. Um, well, I think so. You mean computational performance or from a result? Okay, yeah. Mhm. Mhm. I think that depends on the goal. Like maybe the goal is to for example, have very small oscillations, and also the movement, the minor movement of the pole that we have, it should be very smooth. Probably in that case, we can define velocity and acceleration terms. Uh, yeah, I'm not sure. I think this it depends on the problem, and for our problem, we don't care about how smooth the pole moves. We only care that it's straight enough, and theta is probably within a limit. So I think it depends on the goal, and probably from results point of view, I don't know because I haven't tested. Maybe some of you have tested, could throw some light on that. Yeah. So yeah, I think this is very easy to test. Just you can change the variables, and we can discuss this after this as well. When I'm sharing the code, maybe we can try that out if time permits. Okay. Now let's talk about policy. So the policy, to reiterate, would be a mapping between state and action, or a probability of selecting an action given a state. So for that again, the state and action should be fixed so that we can define a policy. So yeah, let's take the state again as x and theta here. So to make it simple, uh, the policy should be such that it should, I mean, again, try to, if the angle is greater, then it should try to minimize the angle, and if the angle is less, then it should probably keep it at that angle. So all of these things are towards one particular goal, and I think we can individually define it easily if we understand, if we always take into account the overall goal. So any ideas regarding policy? Mhm. Yeah, that's good. Yeah, that's totally good. Yeah, exactly. Yeah, yeah, that makes sense. That's totally valid. Yeah. Any other policy that you think of? And don't worry if you like, if you're not sure, just make wild guesses. I mean, we are all learning here. Nobody is judging you. Okay. So it's kind of similar, but are you talking about like the rate of change of theta? Okay, so I think it's the same thing, right? If theta is Mhm. Yeah. Hmm. Yeah, yeah. Okay. All right. So now let's go to the solution that I have prepared. And to be honest, I'm not an expert at reinforcement learning either. So if you have any new suggestions or think that this might not be the best, and we can probably define states in a new way, feel free to suggest, and we can all learn from it. So yeah, so the way that I've defined the state is x dot, also the velocity, theta, and theta dot the rate of change of the angle. X is the cart position, x dot cart velocity, pole position, and the pole tip velocity. uh, and another small concept that I want to introduce now is that of state space. So state space is nothing but the range of allowable values for each state variable. So for example, we know that x is defined from -2.4 to +2.4. So this is x minus 2.4 to 2.4, sorry. And x dot, the velocity of the cart, and the pole tip velocity can be anything from -infinity to infinity. And the pole position is -41.8, it's in degrees, and to 40 41.8 degrees. This is the range of the pole position, sorry. Yeah, so this is state space. Do you can some of you realize why defining the state in such a way could be problematic to implement the reinforcement learning problem? Uh, uh, just to point out again, in reinforcement learning, we go step by step and reiterate, define state, action, and reward at every time step. And so, do you think like defining the states, or there's something that could cause some trouble here? Sorry. Yeah. Mm-hmm. Yeah, so that would head in the direction of selecting a value function, but I'll cover that in the coming slides. What if we don't get a desired result in the end? So the thing is that we have to define the rewards such that it should, yeah, we have to define the rewards accordingly. And so we basically play with these particular parameters again and again, like action, states, and rewards, and maybe we change how we define it, and in the hope that we will get good results. And I don't know, maybe there's a science behind it, but what I understand and how I have used it is that I always experiment with these variables and try to see like which particular combination gives us the best result. So in defining it, yes, we do trial and error. So for example, maybe you don't need to define x dot and theta dot, right? Maybe you need to. Okay. Okay. Sorry. Yeah. So these allowable values are, yeah, I think these are just predefined based on this particular scenario. So it wouldn't make sense that the cart moves more than yeah, a particular range, right? So this is based on that. And same, maybe there's a limit to the angle that the pole moves. Yeah. Yeah. Sorry, I understood in a different direction. Okay. All right. Yeah, and the action is, I think this is like a very simple problem that I've taken, and most of you already guessed the solution to this. And so, except that the action is actually defined in like as just moving one step left or moving one step right. So yeah, I think that's how you guys also defined it. And the reward is, again, I've taken like the simplest thing possible, that so we know that the episode would fail, episode would be over and would be successful when we have greater than 200 steps in which the pole is straight, right? And so imagine that it is straight for 200 episodes, and for each particular time step we give a reward of +1. So at the end of it we would get a reward of 200, and this would be a good indicator that we have successfully finished the task, right? And again, you can also definitely define it as maybe you define +2 for when it is within the angle, and -1 for when it is outside the angle. So yeah, there is multiple ways you can define this. So how I've defined very simply is reward of +1 every step it keeps theta less than or equal to 12 degrees. Yes, and the goal would be reached when running average value of rewards is greater than 195. This is the minimum that we can have to define it as successful. Yeah. Uh, like in a few steps in between, you mean? So, so no, actually, because the way that we have defined is, it's that the episode would end whenever it's greater than 12 degrees. So, for example, maybe on the second step, the angle is greater than 12 degrees, and then the episode would end in just two steps, and so we would have a reward of very less. So, of course, I mean, that's with reinforcement learning, the reward is always sparse. Yeah, so like after, uh, I don't know, don't want to put a number to it, but after a lot of states, a lot of like failed experiments, maybe we'd have a few ones that would reach us, and those, and that would be the result for us, basically. Okay. Yeah, yeah. So talking about policy now, if the, yeah, policy is also like very simple in this case. And if the pole is left of the center, then we move the cart left, and if the pole is right to the center, then we move it right. Just like simple balancing. And now let's cover the algorithm. And before covering the algorithm, I want to cover a few basic concepts here. So I asked you all like what problem we could have with the state spaces. Like one problem which is not very obvious when we view it for the first time is that the state spaces are continuous, right? So it can move from minus 2.4 to 2.4, and there are infinite values in between, right? And that's a huge problem because at every time step, how are we going to define these infinite values? So the state variables are changing continuously over time, and this is a problem for which we have several advanced reinforcement learning algorithms as well. So in today's case study, I'm taking the extremely simple solution that is possible and was used before we had actor, critic, and other approaches. So we take this state variable, let's say x for example, and it ranges from minus 2.4 to 2.4. Of course it's finite, that is, it is bounded within a range, but it is continuous. And the idea is that we divide it into 10 equal buckets of size 0.48, such that if a value of x lies between let's say minus 2.4 and minus 1.92, then it is allocated to bucket 1. So now you can see that the input is not infinite. The input space, the state space is not infinite, but it's discrete in the sense that we have only 10 buckets to represent it. So does it make sense? Does it give an idea of how this could be easier for us? Yeah, but it would also not be possible to implement a continuous state space, right? I mean, we have to define a time step. So, so since there are an infinite range of values possible, it's not really possible to define it. So we have to find a way to discretize it or use other methods which would be more advanced for today's tutorial. Um, but that would also actually have we would have like compare the number of states we would have. Uh, for example, like the values would be way more than if we just had 10 buckets. Yeah, so this is basically to simplify our problem, and so that it can take less computation and can be easily implemented as well. Yeah. Uh, so let's move on to the next concept, which is state value function. So we need a way to judge how good a state is given a particular policy, right? So let's say this is a state that we have, and based on a particular policy, which is nothing but probability of selecting an action. We get an action from this state, and so what we want to know is how good this particular state is. And for this I just want to cover another small concept called expected return. And okay, I think I've like kind of not used the right links here. Yep. So the expected return is again let's have a look at the goal of the agent. The goal of the agent is to maximize its uh, overall reward, right? That's the whole reinforcement learning problem. And the way we are defining rewards is that we are adding rewards overall time steps. So t plus 1 would be, for example, the reward for the next time step, and rt plus 2 would be for another time step later. So these are all the future rewards, and these are added, and this added value is what is called return. And so what we are doing is that we want to maximize this particular return, and t here is the terminal state, and we know that at the terminal state the episode ends. And another thing is that we want to give more value to the rewards that we have in the next state uh, compared to the rewards that we have in the far future, right? Because the future is very uncertain. So we know for sure that in the next time step, for example, we can have a good reward, but in the future, for example, we don't know which state we would be in and what set of values we have taken. So we can't rely on the future rewards that much. So we want to have a discount factor. So in this equation we just multiply with gamma for every next step, basically. So the more further away we are considering the results, the less reliable they are, and so we want to reduce the reward value, right? So this is how we define it: rt plus 1 plus gamma into rt plus 2. So gamma would be less than 1, and that's why it would be reduced, this particular reward. And as you can see, gamma square rt plus 3, this will be again reduced, and so on, and for the final state the reward would be 0. So that's how we define the expected reward. And why this is important to us is because we want to know the value of a state. So let me explain how all of this is linked. So uh, so this state value function gives the value of a state under a policy pi. We know what a policy is, and this value is an indicator of how good a state is for the agent. So what does good for an agent mean? The most important thing for an agent is to accomplish its goal, and for that it has to maximize its expected return, right? So return is just these added rewards, added discounted rewards, right? So now this equation should make sense. The value of a state under a policy pi. So this policy is defined generally by this symbol pi, and this it's the expectation of the return given this particular state. So for this particular state, what is the expectation of this return? So again, as we define this return, this is nothing but rt plus 1 plus gamma rt plus 2 plus till rt for the terminal state. So we want to maximize the expectation of this, right? So this is another concept that we would need to understand the algorithm. Yes. And now let's look at the algorithm, and don't worry if some of these things are not clear. Everything would come together once we visit the code. So in the algorithm, it's such that we will initialize the policy in the beginning, and we will initialize the value function. These are just initial values that we provide, and for a certain number of episodes which we define, we initialize the environment. So the state action, and just giving an initial value to this. So for example, maybe we give I don't know, 0.5 2x and some particular value, maybe 0.5 or 0 to this pole or something. So we define the environment, and then for each state in one particular episode, now is where we are updating things. So we take this action according to a given policy, right? The policy is such that uh, as it moves right, the card should also moves right. And based on that, we would define action. And action, as we mentioned, is just like 0 and 1 is how we define it. So we would take the action after defining it, and we would get the reward and state, because the state would change, right? After we take an action, it would move, and so x, theta, everything would change. We get it, and then we set the current state to this new state. We just update it, and then we discretize also separately the pole angles. And if this angle theta is less than 0, then we move left, else move right. This is again defining the policy separately, which will be called in that function. And we define a number of goals, and we print the value function for all of these 10 states. So alpha is a learning factor. I think I missed one of the concept slides. Sorry, this is not Monte Carlo prediction, this is temporal difference. I just wanted to show this particular formula here. So I mentioned that we want to have a value of a state. So this is using temporal difference. We calculate return after each time step. So this is after every single time step we calculate the value. So we have an initial value, right? We initialize the value function, plus we add a learning rate to it, and then this is the expected return for this particular state, minus this minus the value function. So this is our formula for defining the value function. And here we have just expanded gt is equal to rt plus 1 plus gamma vst plus 1. So I'm not going to cover the derivations. I think today, after I discuss the code, we also have a brief theoretical concept discussion, so we can probably discuss this in more detail. But for the purpose of the code, we just need to know what this formula is and how it is being used. And this is just the temporal difference error, which is defined by the next reward plus the discount into the next value and minus the current value. Okay, all right. Okay, so now I'll go to the code, and for that I have to just give me a moment. Okay. Okay, can someone just say something? I want to quickly test, because I'm switching system. Basically, it's on Ubuntu where I have the code. No, I'm not able to hear. Once more, sorry.
Is it audible now?
Yes, it is. Okay. All right. Okay. Just give me a moment. So my screen should be visible now. Okay, is my screen visible? Hello? Yeah, okay. All right. So you should be able to see this code. As you can see, it's very simple to implement. Um, and hopefully everything would make sense, and we can change stuff here as well. All right. So I'm using here OpenAI Gym package, and using this, it is very simple to implement. So I've defined a policy, a simple policy here, and the action is equal to 0 if state is less than 5. Uh, Now, does this make sense? Action is equal to 0 means that moving left, right? And action is equal to 1 means moving right. And so the state less than 5, so we saw that we have discretized the state such that it is divided into 10 buckets, and when it is from buckets 1 to 5, and when it is like the next 5 states, so for the first 5 it is towards the left, the angle is less than 0, and so we would move the cart left, right? And for the next 5 buckets, if our state is greater than 5, greater than equal to 5, then we move right. Does this make sense? Hello? Okay. Okay, yeah, so as you can see, it's very straightforward to implement, and uh, so we define we define our environment, and we have a cart pole environment already set up, which has all these states, actions, and the state space, action space already defined, so we don't need to do anything. And alpha is learning rate, is we have taken zero point 0.1 here, and gamma, the discount factor, is 0.99, and this is again this is discretizing the states into 10 buckets. Now this is the value function v, and we have initially set the value function of all the states in the range of a total number of states. All the states have value 0 initially, and now is our main reinforcement learning thing happening. So for I in range of number of games, the environment is reset. So this is like the resetting the environment initially and giving it the initial value, and done is a variable that we have set to false, and while not done, that is while done is true, we define this state in this range basically. So observation 2 is basically here referring to the state, and so everything we get is from env.reset. So env.reset returns the state, action, and reward, right? So the observations second part, this is giving us the state value which we are discretizing or digitalizing, and then we just make it go through this simple policy. So state is the input, and depending on what the state is, we get this action output. and then we take the next step, and we again record the next observation, the reward, whether it's done or not, and info. And again we discretize the next state, and then we allocate to the next state after we have defined the value function. So here the values function is again the same equation that we have had, right? And at the end we just print the value. So let's quickly run it. It's a very straightforward code, and yes, so we now have it. So what we printed was that we printed the state and its value. So we are trying to make sense of the value function now, right? So for a particular state that is 0, a state that is 0 means it is towards the left extreme of its limit, right? And so its value should not be good, because our goal is to keep it as centered as possible, right? And so if it is like collapsing, it's about to fail, so we should not have a very good value, so we have poor value here. And at the same time, let's look at the 10th state. This also has less value, right? And the reason for this is again the same. It is kind of it is collapsing towards the right side. It is about to fall, and this is not the ideal state towards our particular goal. And as we can expect, the middle states 5 and 6 have the most values, right? And so this thing should make sense now how it is. So yeah, does anyone have any doubt with this particular code? Now this is a prediction problem, and in the next uh, probably one of the few meetups I can also explain it using Q learning, how it is done. But let's stick to it for now. So does it make sense, or if anything is unclear, just let me know. Okay, so does that mean that we have no doubts and it's clear, or it's not clear at all? Uh, okay, so it's actually probably not clear. Maybe let me go through it again, because okay. The best way is to actually run it and see it. Maybe let me also try to env dot render. Let me see if it actually shows the state. Yeah, I should have shown this. So here it is trying to keep it within it, within a particular range, and I don't remember how many steps I defined there, but it will continue for the number of steps that I defined, and at the end we would have the result, which is not the best but decent enough, as this is a toy problem that we are handling right now. So yeah, it's just going to keep trying. Okay. Yeah, so to just quickly summarize, the whole idea is that that we have this agent, and it is taking a particular action and changing the state of the environment. So the state of the environment is represented by the movement of the cart and the angle of the pole. Our goal is to keep the pole in a particular range that is straight, and let's go into this first, the main part, and then I can see how tell how it links. I know it's a bit tricky to grasp in beginning, but you will get used to it. So yeah, so the state discretization, divide, making the continuous state discrete. This is what this step is doing. Defining the action. How are we defining the action? We have defined a policy such that when it goes left, we move the cart left. When it goes right, we move the cart right. So that's very simply the action. And then again, we take a step, we take an action, either move left or right, and then the state changes. Observation, reward, done, info. And yeah, this is again the digitization of the state, and this is the main thing, the value function that we are updating, so we know if the state is good or not. So that's the whole idea. I can share this small script with you so you can try it on your own, and just let me know if you have doubts or anything. Yeah, so if we have no doubts, we can move quickly to the next part, which is understanding the theoretical concepts. And depending on the time and interest, we can cover few topics or several ones. Okay, so I'll just quickly again leave and join. Okay. Mm, all right. I hope my screen is visible again. Okay. Yes. So I'm audible, right? Okay. Okay. Sorry, I'm switching systems, so I need to confirm every time. Yeah. Oh, okay. Hello. 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 Is it better now or is it the same? Hello. Okay. Actually, yeah, I'm on my headphones. I couldn't connect the microphone today, otherwise it would be louder. But it's still understandable, right? Okay, so let's move on to the next part. Before that, let me ask you how many of you are familiar with reinforcement learning, and how many of you it's a totally new topic, and depending on that we can take the topics. Okay. Sorry. Okay. Okay, all right. Yeah. So the idea is, let me quickly share and then let me know what you think about it. So the idea was that since we are starting with this, of course, there's a lot of stuff that takes time to understand and also explain. So we can take few of the topics. Like we did for the computer vision session, we can take a few of the topics each. Few people can take multiple topics and just try to explain briefly. You can. There are also some topics that we covered today. Uh, for example, you can take the reinforcement learning problem and try to explain everything in your own words. So if there's something missing, everyone can also understand. And temporal difference, what it is, model free learning and model based learning, Q learning, temporal difference. Okay, I've put it two times here. Okay, anyway, expected return. So this is a simple topic. Markov decision process is a very simple one. So actually, these are the very fundamental topics that I've taken. State value function I already covered. So just I think what we should do is let's take up a few topics of this, each at least one topic everyone can take, and we can just probably take 15 minutes and watch one or two videos or take a PPT online and understand it, and then explain it. And even if you don't want to explain it, or are not comfortable explaining it, that's fine. And we can take lesser topics. So what do you guys think? The idea is to have some good understanding of reinforcement learning, so we can have another multiple reinforcement learning sessions with other topics. So so I mean actually right now, but whatever you are comfortable with, basically like we did for the computer vision meetup. The idea is that you don't need to know anything. Yeah, yeah. So I also want to have this some concept discussion at the end. Maybe we don't need to do a lot of. Maybe we can just take three or four topics of this. But since we are like, yeah. Um, no, I don't. I think it's not that difficult. Once you understand it, maybe starting it can take some time. To actually understand the whole how the whole system is working, it takes some time. Uh, but apart from that, I don't think it's too complicated or anything. Yeah, yeah, yeah. And you don't need to, for example, I have taken mostly theoretical ones. So model based reinforcement learning, model free. We just you can quickly find out what the difference is and explain state value function. I've already explained, and Q learning. Probably you don't need to give the whole algorithm or explain with formulas and details. Just give an overall idea, or maybe how it is different from temporal difference. Anything, I mean, anything you can figure out in 10 to 15 minutes. Sure, sure, sure. Yeah, sure. I mean, there's no compulsion, no worries. Yeah, don't feel pressurized. I mean, the idea is that if you if you search for it and you have to present it, then you would be forced to learn, right? So that's why this is also effective. So how many of you are want to participate, and how many of you are comfortable with at least one topic? Let's just take one topic each. There's pure silence. Sorry, Apur. Mm-hmm. Okay. Okay. Sure. All right. Yeah, that makes sense. So anyway, you have seen the topics. I think it will be easier as well next time. So you can probably do some homework and then present. I think that would be easier for everyone as well, right? Okay. Yeah. Perfect. Sounds good. And another. So there are two options that we have for next meetup or the subsequent ones. Either we can do this thing, the whole session on theoretical discussion, or we can take up another problem, or we can also rediscuss it, right? Maybe you can have a look at it and you have doubts, and we can rediscuss it as well. Okay, let's do one thing. Yeah, just you can I'll give you the Python script. You all can try it out on your own, and then let's do a theoretical discussion on the concepts. So next week we can do like purely theoretical discussion, and we can understand. So for example, if state and observation is not clear or an expected return, let's have a discussion next time. So it's very simple. Just OpenAI Gym and NumPy is all you need. Nothing more. Yeah. Yeah. So this is like a very basic one that I've taken. Uh, yeah. All right. So it's fine. We can discuss the concept next time. And yeah. So this is something that I made a slide of, like write this code yourself, run, and maybe show results. You don't need to show results, just for your understanding, and this is optional and up to you. And yeah, so a few references I can maybe tell you that for beginning it would be great. I mean, just a disclaimer, I'm not an expert myself. My thesis is on this, so I have to um, study and get involved in reinforcement learning, so I can recommend a few courses. So there is this channel by Dr. Phil on YouTube. Just search Phil reinforcement learning or something, and he has like really uh, programming explanations of all the reinforcement learning algorithms. But before that, I would highly recommend you to check the Deep Lizard YouTube channel. And yeah, I've seen. Mhm. Yeah, I've seen like I think one or two of those, but yeah, I get which channel you are referring to. And yeah, so I think this Steve Brunton or Burton, sorry. Okay, all right. Yeah, and I think these David Silver lectures, Steve Brunton, and Deep Lizard, these are for theoretical stuff. Deep Lizard would be a very good starting point because it would be like 5 or 10 minute videos and really good explanation. So I can recommend this thing to begin with. But plus, if you want to like practice, then OpenAI Gym is the best way to start. And there's this spinning up .openai.com. This is a very good and detailed reinforcement learning resource and goes all the way from beginning to advanced in understanding research papers and stuff. So this is something that I'm also doing to some extent currently, and I highly recommend this thing, especially if you don't just want theoretical knowledge and also want to implement. So this would be a good resource. And yeah, so at the, I think, last few pages, it has actually listed all the research papers and all the algorithms in a very organized way, and also probably given some tips and advices on how you can learn more. So it's like all the way from beginner to however big you want to be in reinforcement learning. So this is pretty good, and this thing I really like by Dr. Phil YouTube, because it's actually not beginner friendly, but after some time it's probably the best way to learn, because it actually guides you through the code step by step. And a part of what I'm sharing today, especially the code based, the theoretical stuff I've referred from all over the places, but the programming stuff is from a course that from a Udemy course that this guy is also offering. So this one is also pretty good. Yeah, and yep, that's it for the project. Let's move on to the quick feedback. I don't know how much of it was clear, but I'm pretty sure you would get some idea today, right? What are your feedbacks and also suggestions for presentation? Maybe you can briefly give that. Uh, and also, I have organized this Discord channel a bit, so there is now a separate feedback channel. So on Meetup feedback, if you could give some suggestions for improvement, I think that would be really helpful, because yeah, I'm not sure if this was understandable today. Yeah, machine learning with Phil. Ah, yeah. Okay, you're right. You're right. Okay, yeah. Thanks for pointing out. Yeah, it's machine learning with Phil. Yeah. All right. So yeah, any feedback for the session today, and if you want something, if you want to discuss something in less detail or more detail or different topics, anything. Okay. Yeah, and also if you want to give your feedback later, I mentioned we have this feedback section and meetup feedback channel. So if you're comfortable to write later, just if you could write it, it would really help. And for the project process, so I want to actually keep this project process as standard. Let me show you how I've defined it. So after defining the goal of the problem definition and brainstorming, so I'm just carrying this with one of our sessions, like some of you remember with deep learning. I think this one was everyone liked this brainstorming session, and today also probably yeah. So let's keep the brainstorming session and project or case study solution. After that, algorithm plus code and task allocation. So is there any suggestion on how we can make the process so it's easier for anyone to understand and get involved in this? Any suggestions are welcome. Okay. Yeah, because I mean, I think this coding part was missing in our previous discussions as well. I think just Shujat shared one of the times, and probably a couple of times more, but generally we didn't have thorough code discussion. So, because I mean, ultimately you have to program this stuff, so if you don't know the programming, then that would be a problem. So, that's the idea. Okay, and also regarding this thing, if you have any feedback, just feel free to write. And yeah, let's do a quick introduction session before we wind off. Okay, yeah, I feel like I already know you all, but for someone who would be new, maybe just quickly you could tell your name and uh, where are you from and what your interests are and stuff. Let's start with Aditya again. Okay, awesome. Alina? Mhm. Okay. Oh, nice. Interesting. Yeah. Okay, that's cool. Yeah, do you know Japanese already? Oh, okay, that's cool. Yeah, I've done N5. No, I didn't actually give the exam, but I've taken the course N5. So yeah, yeah, yeah. Okay, awesome. Yeah, Kanishk. Mm-hmm. Nice. Is this the first time that you're joining, Kanish? Okay. So how did you get to know about this server and how did you find today's session? Ah, okay. Mickey Mouse Labs. What does it do actually? I've seen some people from Mickey Mouse Labs on LinkedIn. I think I'm connected with some people, but I don't know what is it specifically that you guys are doing. Okay, interesting. And where is it located? Hello. Okay, I think we lost connection to him. Yeah. Okay, Srinivas, welcome again. Hello, Srinivas. Okay. Okay, okay, okay. Okay, sure, sure. So good to have you this time. And before we leave, I just uh, want to have a quick announcement. But also before that, any other thing that you guys are like struggling with and would like to discuss, like you could just probably casually let me know, and if I can probably include some sections on the server that would help. I can see that like on the server there are lots of people asking for ROS help, and not a lot of people answering, but I think ROS is something that people definitely need help with. Mhm. Okay. Yeah, if you have any like suggestions or anything you would want to any other specific event you would want to do, or like for example some of the guys were doing this uh, ROS discussions and stuff, or anything, just let me know. I can see if I can organize something. Yeah, Apurva, you were saying something? Mm-hmm. Mm-hmm. I mean, sure. I mean, whatever actually is helpful for the people in this server would be applicable to the server, right? So, so for me, it would not make a difference. I can make a separate channel, and if you want to have like admission related stuff, like feel free. I mean, what's stopping you? Yeah, so I can. Yeah, yeah, yeah. Mhm. Yeah, for sure, for sure. So, like, do you want me to make a separate section on admission related stuff or something? Okay, okay, okay. So, mhm. Mhm. Hmm. Yeah, exactly. Yeah, that's true. So, I mean, what I think all of you are pointing to is something related to probably guidance regarding admissions. Maybe someone who is already admitted some place and can guide you through writing motivation letters, I don't know, or something like that. So, I mean, yeah, I mean, we have a good community, so you can definitely reach out to people. I can make a channel and you can write it. I'll tag you on the channel later. So yeah, if you, I mean, we already have so many channels, so for me it's not a problem. I can include a few more. Okay, yeah, thanks for your suggestion. All right, yeah, let's move on to the quick announcement. So it's a really very quick announcement. So to ask you to fill a few roles. So I don't know how to formalize this process because this is something that we need to have a proper system of. Uh, like filling the roles. So currently, this is a role that I defined initially, and Aditya is now like really consistently posting really good news articles on the news feed. So this requirement is already fulfilled, and it's also very helpful. So thanks Aditya for that. And apart from that, the open roles, like this is volunteering to present for the meetup, a project or anything. This is something I sometimes struggle with because it's sometimes difficult to uh, find someone, and it's not always easy to prepare something every week. Every week sharing some idea would be really difficult for me. So I would really appreciate if you could volunteer. I think this is the uh, major requirement currently. Like every week, if some of you could uh, volunteer sharing, or maybe just even come up with a topic, right? Maybe come up with a theoretical idea and just have a discussion. But volunteering to present it would be, I think, helpful for the community, plus also relieve some of my pressure because it's difficult to manage. And apart from that, I'm sure many of you are interested in research and would be reading lots of research papers. Some of you already also mentioned that you would want to participate, but if you want to participate, please write on paper reading volunteer so I can fix your slot. So this is just I want to something that I want to add at the end. And the idea is and all will always be that everyone can participate regardless of age or experience. So that's why I try to keep this whole presentation as beginner friendly as possible. And I will try to make sure that we have the same format, and also even better formats next time, and so that everyone understands everything at the end of the session. So yeah, that's all I want to say, and thanks a lot for joining today's session.